Good morning to one and all. I, Ms. Asha K, Assistant Professor, Department of Electronics and Communication Engineering, Sai Vidya Institute of Technology, Rajan Kunte, Bangalore. In today's class, we're going to discuss about the uh, multiplier. It is the second class of module 2. In the previous class, we learned about the multiplier, and in today's class, we're going to learn about the shifter concept. Just a brief recap of what we have done in the previous class. We learned about the basic architectures. So, what are the basic architectural features necessary to implement the DSP algorithms? The example of the algorithm that we have learned previous class was FIR filter, nth order FIR filter implementation. And also we learned in the previous class what are the main basic computational building blocks of DSP architecture and algorithm. We have four basic building blocks: multiplier, shifter, MAC unit, and KL unit. So we also discussed about the two types of multipliers. One is for signed multiplication and another one is for the unsigned multiplication. So signed multiplication, we had Braun multiplier. For unsigned multiplication, we had Wobbly multiplier. So this is the structure of Braun multiplier and Wobbly multiplier in discussion what we had with respect to speed concept and also with respect to the bus width. So we are considering two n-bit numbers and the product is stored in Z and how to effectively utilize the bus width of the DSP processor with the help of this particular diagram. So, till here we completed in the previous class. In today's class, we're going to learn about the concept called as shifters. So, what are shifters? Why shifters are necessary? So, as we all know from basic sciences or basic electronics classes, from the beginning classes in the prerequisite classes, we know that say if I have any data, say for example, consider the data 100. If I have this particular data, say A3 bit, A2 bit, A1 bit and A0 bit, if I am performing the shifting operation towards the left side, what is going to happen? If I shift towards this left side, I'm going to get the data directly it as 000. This is my left shift operation. Same data if I consider, if I perform the data on this particular data, right shift operation, what is going to happen? So if I perform the right shift of this particular data, I'm going to get here 1 and I'm going to get here 0 and I'm going to get here 0. The 0 will be discarded. I'll place 0 here in the MSB bit. I'll be having next 0, 0, 1, 0 and again 0, 0, 0 and 1. The right shift operation is nothing but the division by 2. I am performing division by 2 operation by considering the right shift operation. Similarly, if I consider an example of 0001, if I perform the left shift operation in the first step, I am going to get 0010. The magnitude of this is 1, the magnitude of this is 2, and then if I shift once again, I'm going to get 0100, the magnitude is 4. If I shift once again, I'm going to get 100, the magnitude is 8. Here, the left shift operation is nothing but multiplication by 2. So this is performing the multiplication operation and this is performing the right shift operation is performing the division operation. So shifters are basically used to either scale down or scale up the operands or the results. So what are these shifters? While performing the addition of n numbers, each of n bits long, I'm performing the addition of n numbers, n different number, capital N different numbers. I'm considering capital N different numbers. So for this capital n different numbers, what we are having here is each n number will be having small n number of bits. The sum can grow up to n plus log capital N base 2 bits long. If the accumulator is of n bits long, then an overflow error occurs. So if the accumulator is of n bits long If any of the addition will yields more than n bits, then what happens? Overflow of the result occurs. Take an example. Say I'm having one number, say that number is 111, that is 4 bit in length, and I'm considering another one number that is also 4 bit in length. If I perform the addition in binary, 1 plus 1, 0 is sum and 1 is the carry, again 0 is sum, 1 is the carry, again 0 is sum, 1 is the carry, again 0 is sum, 1 is the carry. Even though I'm performing the addition of 4 bit number, the resultant output will be of 5 bit length. What happens in this case? If the storage device is of 4 bit only, means the overflow occurs. So this, how to overcome the overflow error? This can be overcome by using a shifter to scale down the operand by an amount of log capital N base 2. So we have to perform here scaling down operation, that is denormalizing, normalizing the results before and after the execution. Similarly, when shifters are necessary during the performing operation of additions, we also require the shifters in case of multiplication. That is, while calculating the product of two n-bit numbers, we require shifters. The product of two n-bit numbers, the sum can grow up to 2 n bits long. As we studied in the previous multiplier, we all know that the sum, if I'm multiplying the 2 n-bit number, the sum can grow up to 2 n bits long. Generally, lower n bits gets neglected and the sign bit is shifted to save the n product. So this, what we are going to do, if the product, sometimes product is of only 2 n bits, if it is not sufficient to store the entire results of our multiply and accumulation unit, so we may neglect the lower n bit and the sign bit will be like for future purpose it will be saved and it is also shifted. So in such cases we use this kinds of shifters. Finally, we also use these shifters in case of two floating point numbers, addition of floating point numbers. So when I am performing, we all know that in the previous module 1, we learned the floating point numbers will have mantissa and exponent. While performing the addition, the mantissa of should be of same length. Say consider I have 2 into 2 to the power 2 and say I have another number, say 1.0 into 2 to the power 2 in such 2 to the power 1. In such cases, this exponent here is 2 to the power 2, here the exponent is 2 to the power 1. Addition of this floating point number will be difficult. What we do now, either consider both the numbers of same exponent, convert this number into 0.1 into 2 to the power 1 and this number is already 1.0 into 2 to the power 1. Scale down this number to 0.1 into 2 to the power 1 with the help of the shifters. So we use here shifters and then later we'll perform the addition of this is 1.1 into 2 to the power 1. So this 2 to the power 1, 2 to the power 1 remains same. This is addition operation. 1 plus 0 is 1 and 0 plus 1 is 1. The final result addition of these two numbers is 1.1 into 2 to the power 1. So in such cases we use shifters. And what we have from the above cases, it clears that shifter is required in the DSP architecture. So for DSP architecture, in the architecture, we require a shifter. A simple problem on the concepts that we have learned in the earlier slide. The problem number one, in this problem number one, it is required to find the sum of 64-bit numbers. Okay, we are finding the sum of 64. Each 64 numbers will have 16 bit in it. 16 bit in it. So each number, say I have A, B, C up to C, D, E, A, like 1, 2, 3, 4 up to 1, 2, 3, 4 up to 64 different numbers I have. Each number will have A15 to A0, 16 bit. Each number will have 16 bit. How many bits should be the accumulator should have so that the sum can be computed without the occurrence of overflow error or loss of accuracy? So what we do in this case, the capital N is n bit, and the sum can grow up to n plus log n bit. If I am having n different bits are of like small n different number of bits, and those like bits are having each are having 16 bit in length, means the formula for calculation of this is the sum of 64 numbers. Each 64 number is having 16 bits in it. The sum can grow up to 16 plus log 64 base 2. Here 16 plus 6 that we are going to get is 22 bits. Hence, the accumulator that I am storing the result should be of 22 bits length in order to avoid the overflow error. Overflow error is nothing but instead of the capacity of the storage, more number of bits are entering. Overflow will take place as discussed in the previous slide. Problem 2. In the previous problem, after calculating the additional bits, how many extra bits necessary, it is decided to have, say we have decided that we will be having only 16 bit. The accumulator is of only 16 bit. I don't have extra bits, extra guard bits. So my accumulator is of only 6 bit. I'll not be having this extra 6 bits. Then what happens? Here, it is decided to have an accumulator with only 16 bits, but shift the number before the addition to prevent the overflow. How many bits should each number be shifted? Again, the calculation goes like this: as the length of the accumulator is fixed, that is of only 60 bit. Uh, Here we have to shift by an amount log capital N base 2. Log capital N base 2 is 6 bits prior to addition operation in order to avoid the condition of overflow. Before multiplying addition itself, before adding those numbers, how many numbers I have? I have 1, 2, 3 up to 64 numbers I have. All the 64 numbers are consisting of A15 to A0 bit. And when I am performing without having the overflow error, if I just wanted to add all the bits, means each bit has to be like shifted uh, shifted 6-bit position in order to avoid the overflow condition. So moving to the continuation of the same problem, if all the numbers in the previous problems are fixed point integers, say we know that we have 4 different types of number system. One is fixed point integers, double precision integers, floating point numbers, and block floating point numbers. In the previous module 1, we have learned all the 4 types of number system. Here we are using these numbers are fixed point integers. So what is the actual sum? Say, to calculate the actual sum, it is obtained by shifting the result by the 6-bit towards the left side. Already we had scaled down the data in the beginning before addition operation. So since what we are doing, we are again performing the left shift operation on the output or the result of the accumulator to obtain the actual sum. Here, the formula is that you all should remember here is actual sum value is equal to whatever is the accumulator content value into 2 to the power 6. If you multiply this 2 to the power 6, why this 6, ma'am? Because in the earlier only each bit was shifted by 6 bits. So again, to compensate that shifting operation, we are multiplying this by 2 to the power 6. Then we obtain the actual sum. So this is about the concept of shifters. So what kind of shifters we use in DSP architecture and algorithm, and what were the concept of like shifters in case of conventional microprocessor system? In the earlier conventional microprocessor system, normal shift registers. Register is a storage device. It consists of combination of flip-flops. Normal shift registers are used to shift the operation. I hope might be in your DSP classes, digital signal like design classes, your those like digital electronics classes, you might have learned your shifting of shift registers, SISO, that is serial in, serial out, then SIPO, serial in, parallel out, then PIPO, parallel in, parallel out, then parallel in, serial out. So these are the different types of shift registers that you have learned, left shift operation, right shift operation that you have learned in your logic design classes or digital electronics classes. So there were requiring only the normal shift register to perform the shifting operation. But what are the disadvantages of this? The disadvantages of normal shift register usage in the conventional microprocessor is it requires one clock cycle for each shift. If I have some n number of shifts, n number of clock cycles are necessary. So that's why it is not desirable to have this kinds of normal shift registers in the DSP architecture. Hence, what we are doing, so we have a specialized shifter called as the barrel shifter. So we'll discuss this barrel shifter in today's class. So which generally involves the normal shift register, which generally involves more shifting operations. So that's why clock cycles required is more, and speed is a crucial. Speed is a very important parameter in case of DSP architecture. To get the good speed of execution of the instruction, we go for barrel shifter. So this is about the barrel shifter. So we use your barrel shifter. So this barrel shifter works on the concept of controls inputs. So control input are necessary to perform left shift operation or right shift operation based upon the control signal. Control signal is going to control the shifting of the data from input side to the output side. So now for an input of length small n, log n base 2 control lines are necessary. This is a formula that you should remember here. For an input of length n, log n base 2 control lines are necessary. Along with that, we also have an additional control line required to indicate the direction of the shift. Direction means left shift or right shift. Based upon this control signal, direction signal and the control signal. Control signals are nothing but the select lines. Here I am performing the shifting of the data lines from input side to the output side. In DSP architecture, we call this as a barrel shifter. A barrel shifter is used for this particular operation. We will learn with the circuit here. This is the input side of the shifter, and these are the output bits of the shifter. Input bit and output bit. Each input is of n bit in length and output is also of n bit length. Based upon the control input, that is whether I have to perform left shift operation or right shift operation. I have a control input here. If control input is 1, then it performs the left shift operation. If control input is 0, it performs the right shift operation. And also number of bit position for the shift, that is control signal. How many like shift position I have to perform, whether only 1 bit position or whether it's for 2 bit position or whether it is 3 bit position. So based upon this shift also, so whether no change means it is 0. I'm not performing any change on the input signal. The input signal is as it is passed to the output side, then the shift is 0. Number of shift bit position is 0. One such example of implementing a 4-bit right barrel shifter, shift right barrel shifter. We are performing here a shift right barrel shifter operation with the help of this particular block diagram we will learn. See, observe here we have the input bit, that is A0, A1, A2, A3, and also we have here the output bits. The output bits we have here is V3, V2, V1, V0. I just wanted to perform here what type of shifting. We are analyzing here right shift operation. When we are analyzing here right shift operation, I have A0, A1, A2, A3, then V0, V1, V2, V3. Just observe here, these are my inputs and these are my outputs. These are the inputs here are, my inputs here are A3, A2, A1, A0. My outputs here are V3, V2, V1, V0. Just observe here that for shift 0, there is no change in the input and output. Whatever input I am just having, the same output has to be observed at the output side. There's no shift operation. If you just see for switch 0, S0 is active. When S0 is active means this is conducting and this is conducting and this is conducting. See, observe here, this A0 is connected here and you are going to get the output B0 is equal to A0. Similarly, your A1, B1 is equal to A1. A1 is equal to output B1 is equal to A1. Then output B2 is equal to A2. So this is your this one. And A3 is always connected to B3 in this case. That A3 is, if there is a connection here, A3 is connected to B3. Coming to this, the next one, shift. I want to perform shift of one bit towards my right side. If I just wanted to perform the right shift towards my right hand side, one bit position, what is going to happen? Switch S1 will be on. So the switch S1 will be having here, I'm going to write it in different color. The switch S1 should be on. So this is switch S1. During the second operation, so this S1 is on. Just observe, since S1 is on, what is happening? Since S1 is on here, what are the outputs that I am getting? Since S1 is on here, my B0 is equal to, B0 is equal to S1 is here, whatever the data which is entering here will appear here. So B0 is equal to A1 is the output. Next, B1, what will be the output for B1? B1 output, what that I am going to get is this, that is B1 output is equal to A2. So this is B1 output is equal to A2. Similarly, B2 output is equal to A3. And since this is A3 is directly connected to B3, this remains the same as it is. There is no change in this case. Coming to the second, I want to perform shift right operation two times. Two, towards my right hand side, two positions. Towards my right hand side, two position means I'll be having here, just see the S2 switch is on. When the S2 switch is on, I'll be having the S2 switch is on in this case. When S2 switch is on, this is on here and this is on here and this S2 switch is also on here. So when it is on, just observe your B0 output. The B0 output depends on A2. So B0 is equal to A2. Hence B1 is equal to A1 B1 is equal to blue color line B1 is equal to A3. Again B2 is equal to, again here also A3. Then B3 is also equal to A3. So we are going to get here. Coming to the next case, that is the last one, when switch S3 is on. When switch S3 is on, so I'll be having here S3 is on. When S3 is on, just observe is B0 is also A3, B1 is also A3, then B2 is also A3 and B3 is also A3. So this is the working operation of a barrel shifter to perform right shift operation. 4-bit right shift operation. So hence, at last, all the bits, output bits are A3, 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 A3. So based upon this shift, that is the control logic. So here we are performing right shift operation on the particular data. Problem number 4 on this barrel shifter. A barrel shifter is to be designed with 16 inputs for left shift from 0 to 15 bits. How many control lines are required to implement the shifter? I told you people to remember in the previous slide, the solution goes like this. The formula for this is the input of length n. How many control line necessary? Log n base 2 control lines are necessary. How much is the input length I have? 16 input length I have. Log n 16 base 2 control inputs are necessary. So log n base 2, so that is 4 into log 2 base 2. Log 2 base 2, 4 into 1, that is equal to 4. 4 control inputs are required to implement the barrel shifter. This completes the shifter concept. So thank you all. We'll move on to next topic in the next class. Thank you.